I'm Ian.
I'm Kyle.
I'm Jackson.
This is our final presentation for United Cerebral Palsy. So,
Are you sure you have some change now?
Is this still in?
oh, we got it, we're good. Alright, so, of the 17 million people worldwide with cerebral palsy, 25%, or 4.25 million people, are nonverbal. That means in order to communicate and interact with other people, they have to use speech and communication devices. So, a lot of issues actually arise here. Because in order to hold up these communication devices while they're on their walkers, wheelchairs, or strollers, they need to use a mount that is often heavy and unwieldy, which can often tip or create balance issues for the person using it. So we were tasked by UCP to make a more efficient mount that will allow for a more lightweight, cost-efficient, and also it will need to be able to grip onto multiple different bars that are in the different models of strollers and walkers because they actually vary in shapes and sizes. So we decided in order to maximize efficiency, it needs to be lightweight, it needs to be easy to use. Also, we need to lower the cost because it's very expensive. And also the versatile grip that actually causes a lot of issues because when they need to switch from walker to wheelchair or any kind of way during the day or in different days, they need to be able to use a one universal clamp.
So as Bix previously mentioned, bars come in many shapes and sizes. For example, the McLaren Major Special Needs stroller is a very common stroller used at United Cerebral Palsy, and this has a square bar which the clamps have difficulty attaching to. Additionally, it's also a very light walker, and it's very susceptible to being tipped by the weight of the mount. This is the K4 wheel walker, which can range from 7 to 19 pounds. It is also a very common walker used at United Cerebral Palsy, and it shares many of the same problems with the McLaren Major Special Needs walker, as it is susceptible to being tipped or veered when the user tries to move with it.
During our first visit to UCP, we were exposed to several of the mounts that are commonly used in the cerebral palsy community. This was one of the most popular ones at UCP. Some of the pros of this one really has a great range of motion. It uses two ball joints, one at the base near the clamp and one near the device holder. This allows us to move in multiple directions at once, along with a central hinge to maintain stability. It's also extremely stable over time due to its steel frame. However, this mount, due to its steel frame, again, is 6.6 pounds, which means it can tip over some of the lightest walkers, which can be as small as 7 pounds. This also costs $325, which for these mounts is not very cheap. And it cannot attach to some strollers as it weighs it down, or is just too large.
So this mount really only has one positive. It's flexible. However, this flexibility also causes issues because when the user is touching the screen, it can actually move farther away from them throughout the day, which can cause some serious problems for use. Also, it's very heavy, and because it moves away, it can be hard to change positioning when they need to.
Lastly, we have this mount. This is one of the last ones we encountered at UCP. The pros of this mount is that it's very stable and rigid. However, because it's very stable and rigid, it often gets in the way. When someone needs to get in and out of their chair or walker, they have to almost move the entire mount out of the way so they can just get in their walker, which is something that you do often during the day. This is a big problem for them. It also does not fit in all strollers and walkers because of the way it's actually attached to the wheelchair or stroller or walker. And so this mount is, while it's great for sturdy and ease of use when they're in the walker, is very hard to use outside of that realm. So design goals. After looking at all of these different mounts at UCP and encountering them ourselves, we decided that the main questions we should be asking ourselves are, how can we, 1, minimize weight, 2, maximize rigidity, 3, maximize range of motion, minimize cost, and maximize user independence and versatility.
With these project goals in mind, we are able to draft our very own solution here. Our solution relies on a box clamp at the bottom, similar to the model from UCP, that connects to a telescopic aluminum tube that allows for increased range of motion along with extendable and retractable length, along with a centralized hinge joint to keep stability while also giving more range of motion, to another telescopic tube, to the device holder itself, which is spring-loaded to allow for the device to be placed inside with relative ease, along with a ball joint to maximize more. We're going to take you through each one of these parts to tell you which problems it solves.
So we chose aluminum as our material because it's a very cheap, durable, strong, and lightweight material that is commonly used in many other products.
So secondly, how do we maximize range of motion? and maximize rigidity at the same time. We've decided that since the ball joints at UCP were not actually mechanically driven, but rather just tight on itself so that it actually didn't move, we decided that making a mechanical ball joint would be best for the solution. By making a mechanical ball joint, which is tightenable with one hand and with one screw, we were able to make a joint that has 140-degree range of motion on each axis, that is this one and this top one. Each one can move 140 degrees and also be tightened at the same time using one bolt that would go from this section to this section. It's kind of hard to see back here. This means that not only could it be used with one hand, but it also can be put in any degree that the user wanted to, and then just be screwed in with one hand, not physically tax it. Secondly, in the middle we utilized a hinge joint. Because of the fact that we already had ball joints here and here, our middle joint really needed to only serve one purpose, and that was to make sure that the mount could just fold. It didn't really have to have too much range of motion or be able to twist, because the ball joints take care of that by themselves. So we just needed a rigid mount, or a rigid joint in the middle. This included with us making a basic hinge joint that you might find on a door or something like that. And the idea is that a single screw goes through these two holes and can be tightened again with one hand, and so that the mount, when put into place, is very rigid, but also has good range of motion because of the fact that the shapes on each of the hinges allows it to have about 140-degree range of motion on each side.
Our next step was to maximize user dependence. For this, our team designed this specific tablet holder. It operates, it's a spring-loaded mount, which allows it to be operated with one hand. These two springs contract and then compress the iPad, which means that you will be able to flip it over, shake it around. It will not come out due to the lips and the springs with the tension. This fits right squarely on top of the mount, along with the ball joint, and allows it to be spun around in almost any direction you would like. This means that any person using it can operate it with both one hand and with relative ease.
And then lastly, our telescopic arms. We decided that since every person and every mount needs to be different for every single person, that our mount needs to be able to change depending on what the user's needs are. As a result, we decided to make our arm telescopic out of aluminum and put springs in the middle so that it can be operated again with one hand. By simply twisting and pulling or twisting and pushing the telescopic arm, you can easily change the length to either short or long. This allows the user to make it in such a way where they can mount it close to the bottom of their mount, or of their walker, so that it doesn't actually tip the walker over, so the center of gravity of the entire assembly is actually lower, making it harder to tip. And so, since these are spring-loaded, they can again be operated with just one hand, either twist or push, and can be adjusted in two lengths.
For the clamp, we decided to use a box grip, which we decided would allow us to have a minimum of 4 points of contact on most types of bars. Additionally, it will be tightened similar to the ball joints and the hinge joint by having a screw, which when twisted will loosen. You place it around the intended bar and tighten it to secure it.
All of these specific parts of our solution come together to form our final mount, which, as you can see, includes all of these parts and solves all of the problems that we found with the previous mounts. Thank you so much for listening. We do have a prototype to show you.
We're most proud of this part. Yeah.
As you can see, this is spring-loaded. This will lock in an iPad. We constructed this in Hawkins Fab Lab. This will allow us an iPad 1. This is measured exactly to the iPad, though the spring loading feature allows it to fit to multiple mounts, especially the ones that we saw at UCP based on the dimensions of this. These will lock in. This, instead of creating our ball joint, we decided to substitute it with a rotating hinge joint here that can move in all directions that a ball joint originally would, though it does lack some of the stability and the elegance of the ball joint. These combine, there's also another one up here. These combine to produce a mount that is movable in almost any direction you would like.
When you move that, how does it tighten?
This tightens across here with this bolt, as Mikhail was talking about earlier. These washers on the inside can then be tightened onto the outside, and the friction of the wood keeps it from moving.
We would have put our ball joint design into our prototype, but we could not make it work in our fab lab. And so this actually would not be a hinge joint on a rotating plate, it'd just be the ball joint.
Okay. And for the ball joint at the bottom part,
Yes.
that you would need a tool to tighten it?
No, it's just one bolt with a handle.
A bolt with a handle?
All the ball joints on the mount are the same, they're just put in different places on the
It can be tightened with one axis with one hand.
Okay, and then the telescoping arms, they were spring loaded, but how do those tighten Is
So
that-
there's
is
little
it like a
notches, so
twist?
you just twist and it will catch into a different
You'll be
track.
able
And you
to-
can just do that with one hand?
Yes.
Yeah,
Okay.
it's just either pull and then twist it into a different track, or pull and then put it back into each track, so. Yeah.
Okay, thank you so much.